today we're gonna learn about two new laws. The first one is the law of Modus Tollens. Let me give you a picture of what it looks like, and then we'll play. Right? Suppose you are given two premises, these two, if P, then Q, and then you're also given not Q. All right. So here we go. So suppose you're given these two true premises. How do you know that not P is true? Right, Hannah? Yep. If you know that this is true, what do you know about Q? This is false. And the only way that top statement could be true is if what? Is if P is false. But if P is false, you're only allowed to write true stuff down. This is true. This is true. It must be the case that not P is true. No, this is called the law of Modus Tollens. It means the law of Modus Tollens. Okay. So in any event, this is the law of Modus Tollens. Let's look at it in terms of a word problem. All right, guys. So I gave you two premises. Danielle didn't study. I'm telling you, if she doesn't study, then she's definitely going to fail. And Danielle did not fail. So what is it that you can conclude? Ben? Yeah, very nice. Danielle studied. Very nice. That's it. That's it. But how would you do this in a formal logic proof like what you did last night? Well, let's just say Danielle does not study is going to be represented by, give me a letter that could represent it. S would be like studying, like Danielle studies. So how would you say does not study? No. What's the word not symbolized in logic? Yeah, the wave-looking thing. So we're going to say that this is going to be not S. She will fail. F. I'm telling you, she didn't fail. What goes here? The tilde, right? Tilde F. What can you conclude? How is this? It's a great, wonderful question. People always ask, where do we use math in real life? It's not some parts of it we use in real life, percents, fractions, addition, but it's the logical, like you can't do math unless you can think in a logical order. And when we go into geometry, it's going to be math like you've never seen it. It's going to be like discussion based. And you can't just you won't be able to just throw out whatever it is that you're thinking at the moment. You know, like, oh, I think this. Like you could do in some other subjects, and people be like, well, that's an interesting point. Let's talk about it. In here, it will be either valid or invalid. You'll be right or you'll be wrong. And if you think you're right and somebody else thinks you're wrong, you're going to use a series of laws or steps or items that came before it to justify. And this is another form of math that maybe you haven't seen before. What's up? No, you will. Oh yeah, we're not going to be. This is like a month worth of stuff. We're totally going to get to like real deal math in a little bit. Yeah, let's use our statement and reason proofs to like justify this out. Instead of us writing out statement and reason, we'll just use S and R. 1, 2. Yeah, that's fine. 1, 2, and 3. Whenever you're doing a statement and reason proof, you got to give the given information, not S then F. Not F, and you also have to write, annoyingly, what? Given and given. Yep. And then finally, what law can you use to justify our final answer? Modus Tollens. My man, Modus Tollens. All right. The second law we're going to learn today is called the chain rule. Let me give you a picture of what the chain rule looks like. Suppose you have something that says P then Q, and in the second premise, you've got Q, then R. Obviously, what can you conclude? What's up? What do you think? It's called the chain rule for a reason. It looks just like another property you might have learned called the transitive property. Go. Yep. You can move to the idea that P then R. You see it? Chain rule, transitive property. You can make this jump. P then Q, Q then R, then P then R. Let me give you a real-world situation where you might see such a rule. It's going to take me a minute or two, though, so I'm going to need time to write it down. So here's a real-world example of the chain rule, right? You start off with a problem. If 2x plus 5 equals 13, right? Then you do a little math. You subtract 5 from both sides. What do you get? You get the fact that 2x equals 8. And then in the next part, you start doing the problem over again. You say, OK, if 2x equals 8, then what would be the next step in your normal math? You divide by 2, and what would you get? Then x equals 4. Then isn't it logical to conclude that if 2x plus 5 equals 13, then x is equal to 4? And so that's where you would see this kind of logic. We've just put names to the process that you guys have undergone, that represents this, I'm sorry. Right? Here's P, here's Q, here's Q again, here's R, and so here we have P and R. So there we go. That's it. So here we go. This is the final culmination of today. We're going to take all of our laws that we've used and we're going to use them to justify this weird-looking logic puzzle. First thing we're going to do is write statement and reason. Here we go. There's our statement and reason. That's where it all begins. What is the first thing that you always do with this stuff? An easy place to start. Sam. Of course, write the given down. All right. So there you go. Here we go. The first thing you got to do is write down all the given information. Now, what are we going to do next? Let's see if we can make any sense out of it. Where are you going to start? Any ideas? My friend. Yep, you. What's your name? Brian. Yep. 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 Oh, yeah. Did you get what he said? Okay. Okay. And what law would justify that? We just learned about it. Not A is modus tollens. Now, there is another route that you can take on the same problem. No. Whoa. Let's keep this so you guys never, ever confuse this. Anything you write down in the statement column, anything you write down must, as a total, be true. Do you understand? If it turned out you found out that A was false, you could only write down not A, because that's true. Right? That's crazy. That's crazy. Now raise your hand if you would have thought like Brian over here. Raise your hand if you thought a little differently. Sarah, how did you think, girl? Yeah. Yep. That's the other way that you could have gone about doing it. If you didn't think like Brian and you thought like Sarah, Sarah would have done the contrapositive of this, right? Do you want to see what it looks like? Let's take a look. Here's an alternative approach. So we're going to take a look at an alternative approach. So Sarah, this is what you did, right? You just flipped over the original, right? And the reason for that you could do that is the contrapositive is always logically equivalent to the original. Then what can you do? Yep. Let's see. Let's see. forgot to record that down. Okay, so here was Sarah's approach. These 3 steps constitute the same amount of work that Brian did. Let's go back to Brian's work for a second. So here we are, back with Brian. Brian had Modus Tollens. Remember Sarah's approach, Sarah's work took 6 steps to complete. Brian, Modus Tollens, you got not A. What's the next step after you get not A? Exactly. B has to be true just by pure detachment. Yep, that's it. So 2 separate proofs. One took 1 less step literally written down, but the mental steps to be able to use Modus Tollens, a lot more in the head. Whereas Sarah's approach, it was a lot more just writing stuff down on the piece of paper, keeping track of it. Both of them are equally fine, both of them are equally appropriate, both of them give equal amount of credit.